I'm pleased to present our first presenter of the day, Klaus Egelberger, a freelance C++ trainer and consultant focused on large-scale C++ software design. He shares his expertise through popular advanced C++ courses around the world, mainly in Germany, but also in the rest of the EU and the US. He's also the initiator and lead designer of the Blaze C++ math library and one of the organizers of the Munich C++ user group. He holds a PhD in computer science. Please join me in welcoming Klaus.
Thanks, Chelsea, for the introduction. So welcome, everybody, to this very short introduction into what is modern C++. Now, you've seen me, you know that I'm here, but I now prefer to share the slides, which means, unfortunately, you will not see me anymore. However, I feel this is not a bad thing. On the contrary, actually, I do need a haircut badly, and so probably it's much more interesting to these slides, not me. So this is now a couple of minutes about the question, what is modern C++? And obviously, I cannot give a complete and full answer, but I can definitely give you a little bit of an answer by actually doing a historical, a little trip into history. However, the first thing I probably should do is to ask a kind of an obvious question in the very beginning, a question that hopefully all of you have an answer to. Who is the creator of C++? Okay, is it Bjørn Strustrup? Or perhaps is it Bjørn Strustrup or Bjørn Strustrup, or is it Bjørn Strustrup? Now, of course, this is not exactly what this will be about. It's not about how to spell his last name, but at least remember who is the creator of C++. So the story of C++ is, of course, a long one. 41 years of history already, and to some extent, it is also the history of Bjørn Strustrup. So let's ask the question, what is modern C++? And for that, let's go back in time to the end of the 70s. And we are now in the Cambridge University of England. This is when Bjørn did his PhD. So at the end of the 70s, and he was investigating a topic with the title of Communication and Control in Distributed Computer Systems. And of course, for that thesis, he had to write code. And at the end of the 70s, of course, there's the question of what programming language did he use for that purpose? And no, he didn't use C, he didn't use Fortran, BASIC, or Pascal. He actually used Simula. Simula, that is the programming language that was invented by these two people, Ole Johan Dahl and Christian Nørgaard. And that is the programming language that actually for the first time introduced class hierarchies and things like virtual functions. That is the language that actually came up with these ideas. And Bjørn loved it. He actually was very, very fond of that because the topic he was addressing was really, really complicated. And everything that helped him to bring in structure to that code was actually very welcome. Unfortunately, there was a big problem. Upon writing his simulator, as he called it, and then putting out on the machines that he was about to investigate, it wouldn't work. It would not work because Simula was pretty resource hungry, especially in the distributed setting that he was about to investigate. And so he had to implement everything again. To avoid terminating the project, and thus having to leave Cambridge without a PhD, I rewrote the simulator in BCPL. Now, if you've never heard about BCPL before, this is definitely not a problem. This is probably a language that nobody needs to know anymore. This is a little example, just to give you an impression. It is very low level, and definitely very much different from what he used before, the Simula language. And indeed, he hated the experience. The experience of coding and debugging the simulator in BCPL was horrible. BCPL makes C look like a very high-level language. And in fact, indeed, he did not like this at all. He didn't write about it, but allegedly, but this is just what he said himself, he lost half of his hair while debugging his BCPL implementation. There may be some truth to that. But still, he definitely was not happy, but he managed to pull it off. He implemented everything in BCPL and finished his PhD. However, he swore not to do that again. Upon leaving Cambridge, I swore never again to take a problem with tools as unsuitable as those I had suffered. A good tool would have similar support for program organization. A good tool would produce programs that run as fast as BCPL programs. A good tool would allow for highly portable implementations. And with this idea in mind, he went to the US and joined Bell Labs. Now, you probably know Bell Labs, and especially at that time, it was a true hub of innovation. A lot of very important things happened there. Amongst other, this is where the Unix operating system was developed. That actually happened at the end of the 60s. However, it probably did not happen as you may imagine it, because indeed, the very first version of Unix was written in assembly. And that this is not a particularly a good choice obviously becomes clear if you get new hardware and have to rewrite the entire operating system again. That ultimately led to the invention of the C programming language. C was introduced as a portable assembler. You wanted to write the code once, and by means of different backends, you could port it to different hardware, to different machines. And when Björn, at the end of the 70s, joined Bell Labs, C was already in use for a couple of years, and people had a positive experience with it. And C had two things that Björn actually liked. It was efficient, so it was close to the hardware, and it provided portable code. It just lacked expressiveness. It did lack the features that Simula provided. And therefore, he chose C to build on that language. And in March 1979, he actually started a pet project with the name of C with classes, which at that time was not really a programming language. It was more like a preprocessor. It would turn, so we'd write code. This preprocessor would turn it into C code, and it would be compiled in assembly. But still, this actually was a good idea. People liked it, apparently. And so after its release in 1979, more and more people used that. Until eventually, so many people used it that things got a little more professionally, and especially the name was changed. So in 1984, the language was finally called C++, which, by the way, was a vote. This was not the decision by Björn alone. Most people voted for C++. Probably because it was now properly named, definitely not C with classes, more and more people started to use that language, more and more. So many that eventually many people were asking for a C++ standard. And indeed, this was the right way to move forward. In 1990, Björn wrote this book, The Annotated Reference Manual, which was kind of the first pure technical description of the language, kind of a pre-standard. And he passed over the responsibility to a C++ standardization committee, which actually, of course, was a great thing. Suddenly there was something ahead, a standard ahead, and more and more people joined the language. But of course, this also meant that the diversity started. And this book appeared in 1994, the so-called Gang of Four book. The Gang of Four book was the first book that actually provided a lot of different object-oriented design patterns. For instance, so you might recognize this as strategy, or that here as visitor. And so let's take a look at how the code at that time actually looked like. And I've chosen a toy problem that definitely fits into this time frame. The simplest one in the book, the toy problem that I'm now looking at, is drawing shapes. So don't throw things at me. I know it's boring, but it's simple too, and everybody's familiar with it. So we want to draw shapes, and we want to implement it by means of the visitor design pattern. So how does this work? So we have a usual hierarchy, as almost all of these design patterns do. We have a shape-based class, and we have circle, square, and probably other shape-derived classes. Let's assume that we have quite a lot of these derived classes, but let's also assume that we're missing operations. And yes, object-oriented programming is actually pretty great at adding new types. So I could easily add a triangle, but it's actually not so great if you want to add any kind of operation. If I would add an operation, I would probably add a virtual function, a base class, and that would mean that the entire hierarchy would have to change. Everywhere I would have to adapt things, implement things, etc. It's not exactly great. And this is exactly what this visitor design pattern tries to approach. I now extract this idea of adding an operation into a separate hierarchy. The base class is called visitor, traditionally. A visitor is essentially an operation on a shape. This visitor has a couple of base classes, a couple of virtual functions called visit, also traditionally, and these operations now need to be implemented in deriving classes. For instance, in rotate or draw. Now we want to draw shapes, we implement the draw visitor. We implement the two visit functions just as we wanted. And then obviously we can already draw any kind of shape. Now, the last thing that we need in order to make it work is an accept function in the right-hand side hierarchy. This accept function would accept the visitor and would just trigger the operation on a given implementation. So circle would just call visit with this, or square would call visit with this too, not just to trigger the right visit function. Now in code, this would actually look like that. We would implement a visitor base class with the two virtual visit functions, pure virtual by the way, that I've just mentioned. We would also implement a shape base class with a pure virtual accept function. And we would inherit from shape circles like this, for instance, which so a circle with radius and potentially many more data members, constructors, getters, and of course also this accept function. We would implement squares too. Again, we would have to inherit from shape, we'd have to implement everything that a shape has, but we also would have to implement the accept function. Now, operations are all derived from draw, from visitor, like draw. Visitor is the base class for all the operations. Draw implements all the visit operations. So I can now draw a circle, I cannot draw a square. And I could draw any abstract kind of shape. So for instance, we could have a draw function that takes a vector of many, many different shapes, circles, shapes, but also potentially, of course, many others. We could traverse all of them and we could draw them in a purely abstract form. Circles and squares do not have to know anything about drawing. They only have to accept a visitor. And so in the main function, we could now set up such a vector of shapes, shape pointers to be precise. We make unique a circle, a square, and another circle. We push all of them into this vector of shape pointers, and we draw them. It works. It actually works pretty nicely. However, of course, there is a couple of things. So this visitor solution requires two inheritance hierarchies, which is, well, some kind of overhead. It also, for that reason, has a lot of boilerplate code. There's many, many virtual functions, both in the left-hand side and in the right-hand side hierarchy. There's many small manual allocations that make unique calls, and there is many, many pointers. Now, many indirections that we have to follow, and both the manual allocations and the pointers definitely mean that the performance is kind of disappointing. It's not really what we would hope for in this context. All right, so this is what it was in the 90s and the 2000s. And this was the time when C++ was, of course, so in mid of 90s, still growing quite considerably until we finally, in 1998, got the first C++ standard. Super success. Yeah, imagine you write a pet project and 20 years later, there is finally an ISO standard. Pretty amazing indeed. And so of course you would expect that now the number of users is just exploding. Everybody wants to use C++, which didn't happen. C++ actually, for some reason, was not particularly popular anymore. And this is now, of course, something that we don't have to go into a lot of detail, because eventually, C++ finally became interesting again. One of the reasons, definitely, was new standards. Yes, indeed. In the 90s and early 2000s, this decline was probably also because there was nothing happening. Really, the language felt a little bit like dead. But then finally in 2011, we got a new C++ standard with hundreds of new features. Hundreds of features that kind of redefined the language. Sturstrup himself said, it feels like a new language. And indeed, it was. It suddenly was different. People had possibilities that they never thought possible before. And for that reason, suddenly also the philosophy of what we do and how we do things changed. So of course, this was not just C++11, there was many more standards. C++14, 17, and for a couple of months now we have a C++20. All of these official standards. Because there's a promise. Of course, it was bad to wait for so many years until C++11 was released. It really felt like the language was dead. But now we get a new C++ standard every 3 years. That is, of course, a big promise. The language is alive again. However, let's take a look at how we would now yield and use C++ today. Because definitely there was a big change. This is the change that we call modern C++. Let's take a look at exactly the same problem, but let's take a look at how we would implement this today. How this visited design pattern looks like today. I would implement circle class again. But do note that there is no base class. There's not a single virtual function. There is not a single pointer here. It's just a very basic implementation of a circle, a geometric primitive. And exactly the same happens to a square. A square is nothing but a geometric primitive. No virtual functions, no inheritance hierarchy, nothing that is out of the ordinary. I would implement operations like that. I would implement, for instance, a class draw, which comes with two function call operators, one for circles, one for squares. And I would abstract from different kinds of shapes by means of a variant. A variant can take a circle or a square. For that reason, now basically represents an abstraction of a shape. So that hence the name shape. We can draw shapes, many shapes, an entire vector of shapes. We can traverse all the shapes and we can visit them, which again reminds you extremely about this visited design pattern. Visit by means of some visitor, which now is draw, and we visit, of course, the according variant. Also, in the main function, things change. It becomes simpler. For instance, we have a vector of shape now, not a vector of pointers, it's a vector of values. And we push back values. We push back circles, squares, and okay, yet another circle. There's no pointers anymore. There is no manual allocations anymore. The code is simpler. The code is easier to understand, easier to communicate to people that are not familiar with all the details of the language. So this modern, definitely value-based solution indeed requires not a single base class. There is no base class anymore. There's also very little boilerplate code. Sure, it's still C++. There is not, it's not like other languages. There is a little boilerplate, but indeed very little, surprisingly little. There's not a single virtual function, and also in this entire solution, not a single manual allocation. All the data is just in this one vector of shapes. Additionally, you didn't see a single pointer anywhere. There's references, which is reasonable, but there's no pointers anymore. And because of no manual allocations, no pointers, no virtual functions, the performance of that is actually fantastic. I don't have any proof, and of course it depends on what you run, but in comparison to the visited design pattern, the original one from the mid-90s, it's actually truly amazing. So that should give you an idea, one idea of probably many, about what changed in the language. So what is modern C++? First of all, it is not an object-oriented programming language. That is just one possibility, one of the many paradigms that we support. It is a multi-paradigm programming language. You've seen OO code before, and now suddenly it's a little more functional, a little more generic. Perhaps there's also a little bit of OO inside. It's definitely still, and it always was, a programming language focused on efficiency and large-scale projects. Absolutely. This is what is the main intention of C++. It's also, interestingly now, a very quickly evolving programming language. There is a new standard every 3 years, but it's definitely more than just the features that these new standards bring. It's definitely a change in focus. We focus, for instance, definitely more on value semantics, few pointers, little inheritance, and definitely a better use of all of these different paradigms. Probably also, of course, because the features allow us to do that. And there's definitely also a focus on simplicity. Less complexity, more focus on making it easier also for the beginners in this language. But probably, most importantly, it is still a lot of fun. So I'm definitely in favor of that language, and I'll probably use it for many, many more years. Okay, so it's one possible answer for the question, what is modern C++? But it's definitely an answer that is giving you a pretty good idea of what it is.
Awesome. Thank you, Klaus. So we're going to go. We do have time for questions and answers. So if you have any questions, please post them into the Q&A box, and I'll be sure to ask them. But I guess while we get things started, in languages as they evolve over time, people with a lot of experience tend to stick to what they know. What are we doing to kind of up-level the ecosystem, number one, on what the new practices are? And number two, how do we bring the whole ecosystem along? Compilers, people who teach this stuff, and existing code bases.
No, you're absolutely correct. This is one of the big problems that we are facing today. So industry is probably 10 years behind what we consider to be the state of the art in C++. And academia is probably even 20 years behind, which is, of course, a problem. So the best thing is to communicate things. And this is what you're doing today. I believe this is a great piece of this puzzle. We're showing people, oh, look here. Actually, it is much simpler today. You can do things differently. There is beautiful new things. Try them. Actually, you will be happy with them. And so also part of my job is to actually give training classes and to help people get a different impression on C++. Okay, I'm sorry, I forgot the second part of your question.
No, I think this is exactly right. I think a lot of times we need to know kind of where the ecosystem is and what we can do. And I think you said education plays a huge role in this. We have a couple of questions that are popping in now, so I'm going to grab one of those now. And of course, you cannot talk about programming languages without comparing them to other languages. So the first question we have is, how do you compare modern C++ against something like Rust?
Of course, Rust is pretty new, and Rust has the big advantage of learning from all the mistakes that C++ did in its 41 years. A lot of the things we have in Rust is actually, indeed, just doing the right thing in comparison to what C++ did wrong on the way. In C++, it's of course now very, very difficult to go back and change decisions because you would break so much existing code. And we're not talking about just a million lines. We're actually talking sometimes about billion lines of code. So huge code bases, etc., and of course many, many, many projects. Rust is in its entirety pretty clever, and I believe that Rust will actually evolve into something that can very nicely coexist. I don't see them as direct competitors. I actually see this as two languages that can learn from each other. Rust now has the advantage that it has already learned, but now C++ can take a peek and learn again. And just yesterday, we actually hosted in the Munich C++ user group a C++ Rust meetup, where we actually talked about the commonalities and how to learn from each other, how to improve both systems and the use of both languages. Yeah.
Good answer. All right, so the next question is, look, I don't know C++. What is its starting point? Which version should I learn first? And do you have any suggestions on a learning path?
You should start with, basically, my suggestion is either pick an easy book, an introduction book, and it's not so important which version it is, just get an idea on the philosophy. It should not be too old, but it doesn't have to be the newest standard. It doesn't have to be a C++ 20 book right away. It has to be a book, however, that indeed communicates the idea of this new C++. There's a couple of very good books around. As a simple suggestion, A tour of C++ by Björn Strustrup is a pretty good starting point, and it's not too much. It's just 250 pages approximately. As a learning path, I also suggest perhaps to take a couple of training classes. Here at O'Reilly, I offer a couple of training classes, 2 so far, and it might give you an idea. It's not long, so it's always 4-hour training classes, but still, you get an idea of how things work, what we do today in C++.
So the next question is, should we consider relearning the entire language? I can imagine people have been writing C++ for a long time. Does it make sense for them maybe to step back and maybe approach a new project, maybe focusing on the latest C++ standard? And I guess to add to that, what things from the C++ history are still good ideas today in modern C++?
So not everything that we did back in the days was bad. Now, also object-oriented programming, like it just showed, is not bad. It's just a little bit overused. It was hyped in the 90s and early 2000s. So I don't think you have to entirely relearn the language. But you should realize that some old things are now not used a lot anymore. We have new approaches. So taking a step back, so especially if you do have the chance to start from scratch, then taking a step back is not wrong. But please do not just rewrite a project because there's new C++ standards out. That is probably not helping you a lot. This may cause other problems, of course.
Our next question kind of piggybacks on that a little bit. It says, hey, I've been writing C++ for a very long time, and they joined a new team that is writing C++ 11, and their question is, why not rename it? Because they feel that it's so different from what they're used to. Maybe can you weigh in on that? Why not name it? Is it so different that it should be considered a different programming language?
It is indeed very different. So perhaps another name would have been nice. But what should definitely not happen, and this is just not my opinion, this is the opinion of a lot of people in the community, it should not happen like in Python that suddenly there's a Python 2 and 3. That would be a split of the community, and that would weaken the community as a whole. So I actually am not so... I feel that the name is important, yes, but not as important as just making sure that there's one path for the language and that everybody is on board. You always have to take a couple of compromises, but I believe this is just always necessary.
This next question kind of talks about the ecosystem. So the next question, Java has Maven, Spring Boot has microservices. Is anything coming to C++ in that direction, maybe to build up the ecosystem just outside of the core language features?
So people today have the ability to pick on the weak spots of C++. Yeah, you're absolutely correct. That is a weak spot, the ecosystem. Please remind yourself that C++ was invented in a time when there was no internet yet, not really. And so at this time was the need to have a big central repository for projects, etc. Just wasn't there. Today, if you develop a language, this is considered absolutely necessary. So of course, there is a lot of things different in nowadays languages, like also Rust has cargo, etc. However, I do firmly believe that C++ will get something like that in not a super far future, because the committee has realized that this is a weak point, a sore point, and it is driving this forward a lot. It is not easy because there's a lot of interests, a lot of different opinions. But if we don't do something here, then of course people will lose interest within the next 10 years. So it is absolutely important. Yeah.
Awesome. So next question. Which of the latest features added to modern C++ made this language more suitable for functional programming?
Okay, there's of course a couple of things that I could say. This variant approach that I just showed is actually a little more functional. However, so is C++ functional or not? If you take a look at the STL, design of the STL and the philosophy of the STL, so part of the standard library, then you do realize there's a lot of functional programming in there already. It's just not the Haskell kind of functional programming. Lambdas may have added to that. We do, of course, get a couple of new features. Perhaps ranges add to this a little, though I think it's not going far enough yet. But this is on the agenda, definitely. There's a lot of people that you want to use functional programming that do believe that C++ should do more here. There's definitely also continued development in that direction. It is an absolutely reasonable paradigm, a good paradigm.
Yeah, I like that. I like that pragmatic approach. I think a lot of people coming from their existing paradigms, you just want to sprinkle in some functional aspects, sometimes in the function body. So you don't want to get carried away trying to morph into a purely functional programming language. Next question. What advances made in C++ compilers to support the modern approach?
The advances made in the compilers. So I believe the compilers just add all the features. Compiler vendors actually have to incorporate all the additions of the latest standards. And of course, they also have to keep up in terms of performance optimization, etc. So compilers themselves probably do not drive this forward, but they definitely, of course, play an important role. Compiler vendors, for instance, make sure that all the features that people want to add are actually realizable. If you could not realize them, then we could not add them to the language.
Would you say the ecosystem, most of the popular compilers that people are using, do you believe that they're all caught up to the latest standards and you don't have to worry about picking the wrong compiler?
So most compilers are actually pretty quick. So there's the three big, which let's name them. So GCC, Clang, and MSVC. These three compilers actually are pretty much up to date indeed. Now, these compiler vendors make sure that the latest features are in there. When C++17 came out, basically all these compilers supported these features right away. With C++20 now, it's a little more tricky because the big features are actually seriously expensive, difficult to implement. So no, they're not there yet, but I believe within the next year, all these compilers will provide the big C++20 features. And so you don't make any mistake by choosing one over the other. By the way, I'm a big fan of using all of them. You should compile your code with more than just one compiler in order to make sure that you're not introducing something that is not portable, anything that perhaps one compiler flags as a warning, the other not. It is always a good idea to use all of them.
We had so many good questions, and we don't really have time to answer them all. Yeah. Where can people find you if they have other questions?
So here on my slide, you'll find my email address. If people do have questions, please feel free to send me an email. Also, if you look for my name on LinkedIn or any social media, then you should find something. So my name is pretty rare. There's a good chance you'll find me right away.